Welcome to another session of differential geometry. Last class we have studied about the Gauss map and a theorem related to Gauss map. Now the theorem says that if S is a compact connected oriented end surface exhibited as a level set of a smooth function, then the Gauss map maps this surface S onto the unit sphere Sn. So we have defined what's a Gauss map, and here what we want to show is that the map is an onto map. For that we have found a curve alpha satisfying the conditions alpha of A is equal to P, alpha of B is equal to Q, etc. And we have seen that this this Gauss map is onto. But today what we are going to do is that we will construct such an alpha. We haven't said anything about that alpha. If such an alpha is existing means we are saying that the Gauss map is onto. So today we are going to construct such an alpha. So construction of alpha. Construction of alpha. To construct alpha, enclose S in the interior of a large sphere S1. Now this is possible since given that S is a compact one. So what you're going to do is first we are having a surface S. So let me draw a surface here. So this is my surface S. Now I want to enclose this inside a sphere. Such a sphere is existing since it's going to be a compact one, right? So I'm taking a circle and I'm enclosing this inside a bigger circle, right? Yes. So after enclosing this into a circle, see my surface is somewhat, it's not lying entirely inside. Let me take another surface. Okay, so that's better. So first of all I have taken a surface here, something like that, one surface I have considered. Now I'm taking 2 points here. This point is P and this point is Q. P and Q. So this is my surface S and this is my circle S1. Now we have interior of the sphere S1. Okay. So we want to say that such a thing is existing. This is possible. This is possible since S is compact. Compact means it should be bounded, right? Now set alpha 1. Set alpha 1 of T is equal to P plus TV. That means this is nothing but 0 less or equal to T less or equal to A1. So this is nothing but a straight line, okay, passing through P. So I'm taking this as something like this. So this is my alpha 1 now. So this is image of alpha 1, right? Now second thing, but where a1 is such that alpha 1 of a1 belongs to S1. So that means see, alpha 1 of a1, so that belongs to S1 means this is my point alpha 1 of a1, this point. Next is, and set alpha 2 of t equal to q minus tv, where 0 less than or equal to t less than or equal to a2, where a2 is such that alpha 2 of a2 belongs to S1. So again I am having a line passing through Q but in the opposite direction. So this is in this direction and this point. So this is my image of alpha 2, right? So this one is image of alpha 2. So now this point is alpha 2 of, we given as alpha 2 of a2, since it belongs to S. Next what we are going to do is we will consider another curve. So let alpha 3 from a closed interval b1 b2 to S1. Another one, be such that here the condition is alpha 3 of b1 equal to alpha 1 of a1 and alpha 3 of b2 equal to alpha 2 of a2. So it belongs to S1. So it belongs to this circle, plus another condition is that alpha, it's starting from b1 ending at b2, and alpha 3 of b1 is alpha 1 of a1. That means it should start from here and it will end from end at this point. So this is your alpha 3, right? Alpha 1, alpha 2 and alpha 3. And here alpha 3 condition is that alpha 1 of a1 equal to alpha 3 of b1, right? And here alpha 2 of a2, this is same as alpha 3 of b2, right? So these are the conditions. Now using these three curves we will define your alpha. Now since such an alpha 3 is existing, what's the reason? Because S1 is connected, because the n sphere S1 is connected. For your n value greater than or equal to 1. Then the function we are defining as alpha, defined by alpha of t is equal to alpha 1 of t, where 0 less than or equal to t less than or equal to a1, and this equal to alpha 3 of t plus b1 minus a1, t plus b1 minus a1, where a1 less than or equal to t less than or equal to a1 plus b2 minus b1. And next one, it is equal to alpha 2 of a1 plus a2 plus b2 minus b1 minus t, comma, here the range is a1 plus b2 minus b1 less than or equal to t less than or equal to a1 plus a2 plus a2 plus b2 minus b1. Now this is our alpha. Now we will state that this alpha is having the required properties. See here, what you have done is you have splitted this interval into so many small intervals. That is, you're starting from 0 and ending with this interval, that is a1 plus a2 plus b2 minus b1. So somewhere here is coming as a1, next is a1 plus b2 minus b1. So here somewhere here a1 plus b2 minus b1, next a1 plus b2 minus b1 to a1 plus a2 plus b2 minus b1. So we are splitting this into 1, 2, 3 intervals. Okay. Now this alpha has the required properties. Where a equal to 0 and b equal to a1 plus a2 plus b2 minus b1. Since we are taking alpha from some closed level a, b, right? So a can be taken as 0 and b is equal to a1 plus a2 plus b2 minus b1. Now continuing and continuity and condition 1 are very easy to check. So here continuity and condition 1 are very easy to check. Continuity follows from this definition of alpha itself, right? And first condition was, when you're defining such an alpha, this alpha should satisfy two conditions. Alpha of a should be equal to p and alpha of b should be equal to q, right? That we can easily see. What is alpha of, first is substituting for a equal to 0, you will get okay, a equal to 0, right? So here your a1 value should be equal to 0, so you will get alpha 1 of 0 will get, right? So what is alpha 1 of 0? You can easily check. Next thing is that we want to check the second condition. So the second condition is from definition of alpha. So let me mention it here. from definition of alpha, alpha is continuous. Alpha is continuous. Also, alpha of A is equal to alpha of 0, and that's equal to alpha 1 of 0. That's equal to nothing but a point P. Similarly, alpha of B is equal to alpha of A1 plus A2 plus B2 minus B1. Now that's equal to alpha 2 of 0. That means Q. Right? Now alpha dot of A. What you will get when you are finding alpha dot of A? Alpha dot of A is equal to alpha dot of 0. That's equal to alpha 1 of 0. That's equal to alpha 1 of 0 comma, when you are finding derivative now, so d by dt of alpha 1 of 0, and this value is equal to PV, and alpha dot of B is equal to QV. You can easily find it out. Thus first condition is satisfied. And also alpha satisfy condition 2. What was condition 2? If T is a point in between A and B, then alpha of T does not belongs to S1, right? So let us have, does not belongs to S. So let us have this discussion here. Since, first thing I am noting, since G composition alpha 1 dash of T, G composition alpha 1 dash of T is equal to del G of alpha 1 of T dot alpha 1 dot of T, right, by chain rule. Now this is nothing but V dot V, which is greater than 0. So G is increasing, G is increasing along alpha 1, and the maximum value of G and the maximum value of G on S is attained, S is attained at alpha 1 of 0, that's equal to P. That's equal to P. And next thing we want to note here is that alpha 2 of T does not belongs to S for T greater than 0. For T greater than 0. Since G composition alpha 2 dash of T, that's equal to del G of alpha 2 of T comma alpha 2 dot of T, right? And this is equal to again V dot minus V, V dot minus V. So this value is less than 0 we will get. So G is decreasing, G is decreasing along alpha 2 and the minimum value and the minimum value of G on S is attained at alpha 2 of 0, that's equal to our point Q. So the third one is that alpha 3 of t does not belongs to S for t belongs to closed interval B1 B2 is true, right? Since alpha 3 of t means it belongs to the circumference of the circle. So since alpha 3 of t belongs to S1 and what we are getting is S intersection S1 is equal to empty. So thus this alpha satisfies all the conditions of our required curve. So this is the construction of alpha. So how we are constructing alpha? First you should take the surface S as a surface, then enclose this inside a circle of larger radius. Now after enclosing, you should define 2 points P and Q and the alpha 1 and alpha 2 or 2 curves and alpha 3 along the circumference of the circle. Now using these 3 curves, we should define your alpha. So like this we are defining alpha. So 0 to A1, see, remember this interval, 0 to A1 it is alpha 1, A1 to this it is alpha 3. Now from this to here it is alpha 2, right? Now this alpha satisfies all our requirements. So show that this alpha satisfies all these requirements. So hope you understood how we are constructing alpha. I'm winding up here. Thank you for your patient listening.